No worries. Okay, where I want to start is, there we go, is with a motivation for why we might really care about looking for habitability in other environments. I think if you read your undergraduate textbooks that some of us teach out of with regards to habitability, there's the story that we like to tell about how life on Earth arose almost as soon as it could when it was given a stable, habitable environment. And we use that to convey an idea that maybe our universe is teeming with life, so that maybe we live in a universe that looks like this, where the number of environments that exist that are habitable, which I intentionally haven't defined yet, and the number of environments that we explore that show signs of life that are inhabited are roughly comparable to one another. And if you lived in a universe like this, your takeaway would be that life frequently arises when habitable conditions are present, and thus that abiogenesis is the norm. But something that I think we're all interested in exploring in our lifetimes is the potential that maybe we live in a universe like this, where as we set out across the solar system and as we look towards exoplanets, that maybe we discover a lot of habitable environments, but in few to none of those do we find signs of extant life. And then the takeaway from this is completely different, which is that when given a habitable environment, abiogenesis doesn't occur. So abiogenesis is the exception. And I think this has profound impacts on our worldview. And so to be able to know which of these universes we live in, you need to be able to do a couple of things. You need to be able to search for signs of life. You need to be able to search for biosignatures. But you also need to be able to search for signs of habitability. And that can be habitability in the solar system, or that could be habitability on exoplanets. You need a scheme for the remote characterization of habitability to know how many habitable environments are out there, and then to also know how many of those environments show signs of life. So an issue with habitability is that it's a wishy-washy term, and I was intentionally a little bit wishy-washy with it on the former slides, in that I think in the solar system we tend to take a more diverse view of habitability. We talk about habitability on Earth's surface. We also talk about habitable subsurface environments on Earth. We talk about the habitability of things like aquifers on Mars. We talk about vast subsurface oceans on icy worlds in the solar system, all of which are wonderful, and some of which we have the opportunity to potentially go to and explore or to sample and bring back to Earth. And so our focus and our language for habitability when it comes to solar system worlds is a little bit different than for people who work on exoplanets, where for exoplanets we are more restricted in the kinds of environments that we might be able to probe. And so for exoplanets, we're much more focused on surface habitability. And so I'm going to do my best throughout this presentation to, when I'm talking about habitability in exoplanets, to say surface habitability. But if I just say habitability for exoplanets, I'm talking about surface habitability, save for some few final slides that I'm going to get to. And so that's why you'll hear exoplanet people sometimes jokingly refer to the habitable zone as the light on water zone or the photons on ocean zone, because we care about where does the light probe down to the surface that we might be able to understand if there's a habitable environment there. Just a quick plug for unpacking these terms and work that I was not involved in. Daniel Pai here at University of Arizona, along with Rory Barnes and collaborators as part of the Nexus Quantitative Habitability Science Working Group, had a recent manuscript up on arXiv looking at the terminology of habitability and how you might define habitability in a way that spans the solar system through to exoplanets. This is a nice graphic from it where they tried to amass a lot of ideas for how habitability should be defined, where they looked at it across a couple of different axes about how comprehensive the definition might need to be or how simple the definition might need to be. But what these authors arrived at was a model that separated out the habitat over here on the left from a metabolism viability treatment. And so their idea was that you have a habitability model that is informed by observations of the system that might tell you something about kind of the thermochemical state of that system. What's the pressures like? What are the temperatures like? Is there liquid water present? And so that's the habitat model. And then separate from that, you have information about organisms that you've discovered right now on Earth that exist in different habitats with different extremes in pressure and temperature. And so you can fold your habitat model together and your metabolism viability model together to get what results in what they call a habitat suitability model or assessment. So a nice way of thinking about habitability. For a lot of what I'm going to present in the next slides, or for the rest of this talk, is going to be really focused on the habitat model side. So how do we probe the conditions of a planetary surface that might tell you whether or not it's habitable, whether or not liquid water could be stable in that environment. I'm going to touch on a few different ways of doing these observations that span ground-based giant 30-meter class telescopes. I'll spend a lot of time on the Habitable Worlds Observatory, given my involvement in that. I have a fair bit of things to say there. We'll also touch on James Webb Space Telescope, and then we'll also talk about solar system missions that have told us things about how you explore for habitability. What I'm going to do is I'll take each of these icons and I'm going to put them in a corner on one of the slides. So if you like completely zone out and then come back and I'm still rambling and you want to know what kind of observation is he talking about, you can look for the spacecraft or the ground-based observatory that's hanging out on the slide. And so the first place that I'm going to start is the classic place to start with a study that maybe you are not familiar with, but is one that is near and dear to my heart, which is a look at data from the Galileo spacecraft from 1990 and 1992. So Galileo was en route to the Jovian system. It needed some gravitational assists to get there. It did 2 Earth gravitational assists and took observations of our planet during those gravitational assists. These are observations from the 1992 flyby. But famously from the 1990 flyby, those data were highlighted in a Nature paper by Carl Sagan, led by Carl Sagan in 1993, where they took a step back and tried to assess their observations for signs of life, and also spent some time not using the words of habitability assessment, but thinking about whether or not there was a liquid present that life might be using. And so they put forth some arguments for habitability, and I'm going to develop those a little bit with a graduate student at Northern Arizona University. We actually went back into the Galileo Earth data set. If you read the Sagan paper, you would get the impression that there were only a few observations of Earth. But if you go into the PDS, there are many, many, many observations of Earth from those flybys. And so we were able to reduce those and have an updated Galileo Earth data set. Ryder Strauss led that work. So what I want to highlight here, and was highlighted by Sagan and co-authors, is the direct detection of surface habitability. And so what I want you to focus your attention on, if the projector does it well, is the diffuse yellowish glow that is happening at this fixed point on the sphere, which is specular reflection off of that globe, and that is what we would call ocean glint. Liquids are really good at doing this specular reflection. And so Carl Sagan and co-authors noted this specular reflection and said, signs that there's a liquid present on the surface. What liquid is it? They looked to the reflective region down here at the south pole of this planet, noted that there were signs of water ice features coming from this south pole region, and so they deduced that the liquid that they were spotting was liquid water. Was one of the arguments that they made. And I would call that direct detection of surface habitability. You have directly detected a liquid on the surface of that planet. They also had data from the near-infrared mapping spectrograph, NIMS, that was designed to work out in the Jovian system where temperatures are a lot colder. And so it had some issues when pointed at Earth. And so this is a NIMS image of Earth in thermal emission, 4.6 microns, that has some dropouts just because of saturation issues. But if you go to some of those pixels that are not saturated, they actually had a spectrum for each one of those pixels. This is what made it a mapping spectrograph. And look at the thermal infrared data that came from those pixels. And if you go to pixels that you know from context images are probing down to the surface or near surface, you can get some constraints on what the temperatures are like at the surface environment. And so those temperatures span, if you look across the disk, say 240-ish Kelvin to about 280 Kelvin that you can deduce by looking at brightness temperatures in those observations. There was a little bit of what we would today call retrieval work done on these observations. We can return to it during the Q&A if you really want to know how they did it. But they did try to figure out how much air was there, but they weren't sensitive to molecular nitrogen. It's not a great gas when it comes to spectral activity, but they were sensitive to molecular oxygen, O2. And so they were able to deduce that there was about 0.2 bar or more of air on that planet. So if you go to a water phase diagram and put that range of temperatures that I just showed you, and that really what amounts to a lower limit on the atmospheric pressure of 0.2 bar, you see that surface environment spans into the liquid water regime. And so I would call this a constraint on surface habitable conditions, is that line of argument. you've confirmed that liquid water would be stable in that surface environment by looking at the pressure and by looking at the temperature. I like to organize all of this onto my little kind of piece diagram of the three ways that I like to think about going after characterizing habitability. And so we've seen examples of two of these, which is the direct detection of habitability and then direct constraint on surface habitable conditions by looking, say, for pressure and temperature. But there are other things you can do that kind of combine models of the environment with observations in a way to try to constrain surface habitability. And so this might be like you have a spectral observation, but you run climate simulations of that world to try to match the spectral observation, and then those climate simulations inform you in some way of whether or not that planet is habitable. I'm going to work through each of these, spending the most time kind of on number one, which is the direct detection of surface habitability. In the literature, there have been a few ways proposed for exoplanets that you might go after directly detecting a liquid, an ocean on the surface of an exoplanet. So you could go after ocean glint by looking at the phase curve for the planet, where at least in Earth's phase curve, as I'll show you, ocean glint does contribute substantially at crescent phases. And so that phase curve contains information about specular reflection off those oceans. You could look for ocean glint both in phase-dependent color information or phase-dependent spectroscopy. As I'll show you, glint has a characteristic color associated with it, and so that might clue you off that there's an ocean on the surface of that exoplanet. Or you could look for the polarizing effects of specular reflection off of an ocean. So you could use polarimetry to try to indicate whether or not there's an ocean present on an exoplanet. So here we're talking about reflected light predominantly. This is a really nice diagram that Sophia Vaughn put together in 2023, thinking about these different processes. So here's the phase of the planet running along the top from full phase to crescent phase. In the top plot here, so the different colors are different wavelengths, spanning red wavelengths to near UV wavelengths. The top plot is just a measure of the total brightness as a function of phase. And then the bottom plot is that brightness in polarized light. So divide the bottom plot by the top plot to get the polarization fraction. In the bottom plot, you have scattering from clouds, giving these rainbow effects. And the glory effects here in the polarized light. Rayleigh scattering polarizes radiation, so it's responsible for a wide range of phase angles for polarizing radiation from our planet. These are all simulations. And then ocean glint contributes substantially to polarization out at crescent phases. So this is just a nice encapsulation of where in phase do these different processes contribute. Let's talk about ocean glint and its dependence on phase. So here's a nice image from the Rosetta mission looking back at Earth, where you can see underneath the clouds a really reflective surface. This is a glinting surface shining back at you. If you've ever watched a sunset on a beach, you've seen the exact same process in action. We set out to quantify the contributions of glint to Earth's phase curve now a little while ago, using a model that was validated against NASA observations of our Earth as part of EPOXI, the NASA EPOXI mission. So what I'm showing you here, the bell-shaped curve is the absolute brightness of Earth as a function of phase. So here's full phase here, and then new phase over here, new phase over here, and then convert that into a measure of reflectivity. I used apparent albedo. As I like to say, there are a lot of albedos out there. You should pick your favorite. My favorite is apparent albedo. If you really want to know why, ask me later, but you should have a favorite albedo, and I hope it's apparent albedo. But this is a reflectivity that's been normalized to a Lambert phase function. So it's divided out the first order illumination effects, which I think is an intuitive way to look at it. We reasonably well reproduce observations, especially from Earthshine, that looked at the visible wavelength reflectivity of our planet. And then I reran those same simulations with the ocean glint effect removed. That's the light gray. And then the difference between those two is running along the bottom, where at these visible wavelengths, so these were broadband 400 to 700 nanometers, ocean glint is responsible for increasing Earth's brightness by as much as 50% in some of those cases. If you go to red wavelengths that have a lot less contamination due to Rayleigh scattering, ocean glint can more than double the brightness of Earth. So it is a substantial contribution to Earth's brightness. Those were forward models. We've recently set out to try to do the inverse problem. So if you hand me a phase curve, can I tell you what processes are contributing in that phase curve? And so the data points here, again, as apparent albedo as a function of phase angle, are brightness observations of our planet from spacecraft and from Earthshine. We fit a model to it, which is the black curve there, but we were able to disentangle different physical processes. And so at these visible wavelengths, we learned that scattering from vertically optically thin aerosols, so things like the Yunga layer or cirrus clouds or dust clouds in our atmosphere are the dominant contributor out of these crescent phases, but that ocean glint also contributes substantially. Like I said, you only expect about half of the brightness at these wavelengths to be coming from ocean glint. If we had data from redder wavelengths, it would be much more valuable because that's where you expect ocean glint to be more dominant. But what we did learn is that these vertically optically thin aerosols that do a good job scattering in the forward direction can serve as a false positive for ocean glint. And there's still work to be done there about how you would disentangle these false positive aerosols from true ocean glint. One thing that you might go after is the color dependence of ocean glint. And so these are simulations run by an undergraduate student that worked with me at Northern Arizona University, Dominic Ryan, showing reflectivity, again, as apparent albedo as a function of wavelength, from blue to near infrared wavelengths for simulations, realistic simulations of Earth that include glint, and then the dash curves do not include glint. And you can see that the glint contribution is much more dramatic out at the red wavelengths. And so what Dominic did is he applied principal component analysis to this and showed that if you do PCA on phase-dependent spectral observations of our planet, that generally one of the top two contributors to why the planet spectrum changes from gibbous phase to crescent phase is a spectral contribution that has the same shape as glint. And so we took this as a promising avenue for using color or spectroscopy to go after surface glint to directly detect surface habitability. Polarization is a developing area, so these are all models that I intentionally haven't attributed to anybody, showing polarization fraction as a function of phase. For this top curve, you need to flip it, you need to mirror it, because full phase is over here for them. But I want to show you, only very recently have observations come down using Earthshine techniques for what Earth's polarized light phase curve looks like. And this is color-coded, so you've got polarization here at 700 nanometers. The blue dots here are the observations that are Pacific Ocean dominated, and the red dots here are observations that are kind of Atlantic, towards the Atlantic, and have continent in them. And the idea is that maybe you would be able to tell a world that has polarization from oceans, from polarization, less polarization from a continent-dominated world. And so there's still a lot of exciting work to be done here on whether or not you can kind of work the inverse problem for polarization as a signature of surface habitability. So let's check the box for the top left here. Let's talk a little bit about direct constraints on surface habitable conditions. So here in the background here, I want to remind you that we're thinking about measuring pressure and temperature to directly constrain whether or not liquid water would be stable in the surface environment. I'm going to provide a quote from myself in 2017, which is that regarding reflected light observations of Earth-like planets, I said, the influence of atmospheric temperature is extremely small. I had a mentor in my life who once told me that if you're going to be wrong, what's important is that you are the first person to discover that you're wrong and publish on it, because then it's an improvement and not a correction. So I want to show you some results from a student that I then went on to work with that actually proved this statement to be wrong, and that I'm glad we proved to be wrong. So this was work that was led by Amber Young, who is currently at Goddard Space Flight Center, was a graduate student with me at Northern Arizona University, where we were thinking about doing retrievals, the inverse problem, on simulated observations of Earth and reflected light as applies to the Habitable Worlds Observatory. And so HWO is envisioned as going from the UV out to the near infrared. These are what a characteristic observation of our planet would look like. Amber imagined different data qualities, so like an SNR of 20, 30, or 50 on these observations, and then asked, what could we learn about this planetary environment? Amber's work was focused on biosignatures, and if you want to go read that paper, it's all about how we might be able to detect atmospheric disequilibrium on Earth-like planets. But what I want to point out from this work is that in our inverse analysis, we actually included a temperature parameter, and we were able to, from those reflected light observations, again, these aren't thermal photons that are emitted by the planet, from those reflected light observations, mostly from thermal broadening of water vapor absorption bands, able to get a constraint on the temperature. Temperature here needs a little bit of air quotes around it, though, because what you're probing there is an atmospheric temperature. And it's kind of integrated through the column of the atmosphere, because you're just kind of looking at the general broadening effects of the water vapor bands. And so there's no one point in the atmosphere that we can assign this temperature to. But we can at least say that these temperatures are consistent with the planet being clement. And generally in these retrievals, ourselves and other authors have shown that both from the widths of water vapor features and the Rayleigh scattering feature, you can get a good constraint on pressure. And so Amber was able to constrain atmospheric pressure on these observations of an Earth-like world. And so from those two data points, you could indeed go to a water vapor phase diagram, plop those data points on there, and argue that this world appears to be habitable. Liquid water could be stable there. A quick plug for a mission that I haven't talked about all the way up until this moment is from our colleagues over in Europe. They're working on a concept called the Large Interferometer for Exoplanets or LIFE. This would use interferometry and formation flying in space to directly image Earth-like planets in thermal emission. Thermal emission has a lot of perks to it in that you're directly collecting thermal photons, so you immediately know about the thermal environment. Also, thermal emission does a pretty good job of helping to constrain the size of the planet that you're looking at, which is something that's a little bit more challenging for reflected light observations. And so work led by Eleonora Alayi, who's also now at Goddard, took simulated observations of Earth that you would get with LIFE. And so these are the simulated observations running along here. On the left is brightness as a function of wavelength through the mid-infrared, applied retrieval analysis to that. And one of the things in their retrieval model is a thermal structure treatment for that planet. And indeed, they're able to get pretty good constraints on the surface temperature and surface pressure of that planet that would put it in the habitable regime. So promising work on being able to directly constrain surface habitable conditions for Earth-like planets. And then the last thing I'll talk about, albeit briefly, is ideas of how you might use models coupled to observations to try to infer surface habitability. And here I'm actually going to turn to the TRAPPIST-1 exoplanet system, and I'm going to look at TRAPPIST-1e, which has a couple of papers that are out on arXiv recently. These are recent transit spectral observations of TRAPPIST-1e. So the data are in black, an atmospheric model is in blue, a flatline model is in orange, Espinosa et al. 2025, and what Earth would look like for comparison. These observations at this point are so noisy that you can't rule one model in or out, and the flat line actually fits these observations perfectly well. So there's no strong evidence for spectral features here yet. They're working on this problem. But what I want to point to is in a companion paper in an appendix, they were trying to do some retrieval analyses on these observations, and they included in those retrieval analyses a thermal structure model that was dry convection in the troposphere and an isothermal stratosphere. And so they overplotted the constraints that they got on the surface pressure and temperature from that assumed temperature pressure model with now a phase diagram of CO2, not water, to show that, for example, using those observations, it seems like it kind of prefers high surface pressures and low temperatures. The low temperatures are preferred because they reduce the extent of those transit features. And so this is an idea of like if you have a thermal structure treatment inside of your retrieval model, maybe by pairing your thermal structure treatment with an observation, you can start to constrain the climate of a planet. So in my last couple of minutes, just a few things that I didn't get to speak about in depth that are some other considerations that we might want to keep track of. These slides will get released, and actually all of my references are hyperlinks. So if you want to download these slides and go check out the references, use those hyperlinks. And so there is starting to be really, there's now a growing body of literature on what you'll be able to do with the ELTs with regards to studying habitability or studying processes that are related to habitability. And so specifically, if you have an ELT that has a reasonably well-performing coronagraph, and especially if you pair that with a high-resolution instrument, you might be able to probe 10-ish habitable zone worlds for signs of biosignatures, and that's a step towards understanding the extent of life in the universe. And so Kevin Hardigree-Ullman led this work in 2025. There's a great review by Ignas Snellen that includes a section on what the ELTs might be able to do for Earth-like planets. This is a developing area kind of as we speak, as we begin to understand what the performance of these observatories are going to be like. I didn't chat about what you might be able to do with regards to constraining processes that are related to habitability. On Earth, we tell the story of the carbonate-silicate cycle as being this long operating cycle that has helped us maintain stable liquid water at our surface over billions of years. And so recent work by Antonin Affolter connected to Habitable Worlds Observatory looked at if you had a statistical sample of many tens of exo-Earths that span the habitable zones of their host stars, could you look for evidence of what form of tectonism is active on that planet? Could there be something like a carbonate-silicate cycle on that planet? All of a sudden, there's been an exploding literature on exomoons. And so this is where I think there is a connection between our solar system, icy moons and icy worlds, and the exoplanet science, which is now that we're starting to talk about detection of exomoons, I feel like a logical next step is what are the remotely observable signatures of subsurface habitability that you might be able to detect for exoplanets? I've talked about surface habitability, liquid water on surfaces. What if you have a vast subsurface ocean underneath some amount of ice? Are there going to be signs that you could look towards to knowing whether or not that subsurface ocean is present? And that's a question that hasn't been well unpacked between the solar system connection and the exoplanet connection. So I'm going to put up a summary here. So we've talked about habitability has kind of a difficult to nail down definition, but it's understanding habitability and how you would remotely sense it is absolutely critical to knowing or understanding our place in the universe. Is abiogenesis common when a liquid solvent is present? We talked about different ways of characterizing surface habitability for exoplanets. I made the point that JWST is kind of now embarking on trying to constrain habitability of exoplanets. TRAPPIST-1e and some of the TRAPPIST-1 exoplanets are when it really boils down to some of our best bets for habitable exoplanet environments that you're going to probe with JWST. So we should certainly be rooting those people on in their endeavors to probe those environments. Talked a lot about Habitable Worlds Observatory and how it's going to be able to probe for surface habitability on exoplanets. And I talked about ESA's LIFE mission and 30-meter class telescopes, albeit briefly. That over there is an updated review that I have on remote sensing of habitability for exoplanets that has a lot of this stuff in it, and you should feel free to download it. And with that, I'm happy to take questions. Thank you.
All right, questions for our speaker, and if I could have our next speaker come up as well.
Wonderful talk. Could you comment on the idea of biosignature gas detection with HWO? With HWO. So in particular, I don't think I heard you say the word biosignature once.
You said it once.
Once?
Say it once.
Yes.
Okay.
So the reason that I don't say biosignature much is because I like to disentangle the habitability characterizations science from the biosignature science. I think you need to be able to do both. And if you blend them too much and let yourself be governed by biosignature detection, you might end up with an observatory that can spot signs of life, but that cannot spot signs of habitable environments. And so I like to keep them separate. Biosignatures is certainly going to be key, if not the central pillar for Habitable Worlds Observatory. So there's a wonderful living world science case that was presented or handed over to Habitable Worlds Observatory that I can say from my involvement on the community science instrumentation team is driving a lot of our thinking about what wavelengths do we want access to, what kind of spectral resolving power do we need to be able to spot a lot of the biosignatures that were digested from that living worlds group. So it is key to HWO, but I am being intentional when I separate it out from habitability assessment.
Hi, Finnegan Keller, ASU. Quick question about sort of the difference between habitable conditions and ones that might be prone to life sort of originating. When you had your first plot up and you were showing sort of the amount of time or the difference between habitable environments that are habitable and ones that we might actually see life in, I sort of had this question occur to me about, are habitable conditions likely going to lead to abiogenesis if just given enough time, or are potentially the conditions that are required for life to begin sufficiently distinct from those that make an environment habitable once life has already started? Is that something that we need to kind of play into our sort of questions of how we frame HWO or not?
Yes, and so could I check my understanding of that? So is that a question about timescales and how long the habitable environment has been present before abiogenesis occurs?
Sure. So I think the two ways, when I looked at your plots at the beginning about like, is abiogenesis common or is it not common? The thought that popped into my head is like, okay, is this a timeline question? Is it just that it requires a significant amount of time of a habitable environment to exist for abiogenesis to occur? Or could abiogenesis be uncommon even if habitable environments are common because the conditions for abiogenesis are sufficiently distinct from the conditions for habitability? So the overall question being, with HWO or other life detection missions, are there different sort of parameter spaces of conditions we need to optimize for to look for the origins of life versus life that currently exists?
Yes. So I do think there's an opportunity that if you know the age of the planetary system well, and so that you might have some constraint on how long the habitable environment might have been present, for you to be able to say with HWO something educated about the timeline for abiogenesis to occur. Now, an issue that I didn't fold into any of this, and that you're getting dangerously close to, is one of stellar ages, which tend to have fairly large error bars on them, and is an issue that is on the minds of HWO people. And that if you want to ask questions about planetary evolution or evolution of life or timescales for abiogenesis, you need a good clock for that planetary system. And so we're going to need really good stellar ages to be able to ask questions like that.
All right, let's thank our speaker.